Good afternoon, everyone. Thanks for joining us. We are live at BeyondX. We hope you are seated comfortably. We have interesting talks going on today. My name is Joe at SEA Design here in Singapore.
Oh, I'm sorry. My name is Lit Hao. I'm the Director of HR at ONG&ONG Group. And well, before we get started, just a very quick reminder to all, everyone on board. Don't worry, your mics and your cameras are disabled as per Zoom protocol, webinar protocol. If you like to make a comment, please click chat. Do chat with us. Yeah, we want to know your opinions, your thoughts. Do put in your opinions in the chat button. If you want to ask questions, of course, there's a Q&A button. So we hope to have a very lively Q&A later just before the session ends. So let us know what you think. If you have any questions, just feel free to share as many questions and thoughts as possible. Yeah.
Okay, just a brief introduction. BeyondX is an annual design festival showcasing fresh technologies and speakers to inspire creativity and innovation, where we invite the most prestigious speakers in their field to share knowledge and developments in the world. For this year, we invited 10 speakers from diverse backgrounds to share their knowledge as we explore the ways smart technologies and digitalisation can inform the future of the AEC industry.
Right, we have a total of 8 sessions over 2 days. We start at 10 a.m. and we close at 4:15. So this is the last session of day 1. And then do join us again tomorrow. We start at 10 o'clock sharp Singapore time. We will end again at 4:15 Singapore time tomorrow. Right. So okay, here we go. So without much ado, let's welcome our speaker. This afternoon we have Mr. Panos Economou. Panos is the founder of Panacoustics in Cyprus. He is in collaboration with SoundZipper in Singapore. Now, having founded his company Panacoustics in 1982, Panos has grown it into the leading acoustics consultancy in Cyprus. In 2009, Panos founded PE Mediterranean Acoustics Research and Development, the acronym PEMARD, PMARD, a company dedicated to addressing the acoustical problems. So now, without much ado, we would like to welcome Panos to share his thoughts, expertise, opinions, and please enlighten us. Yeah. Panos, you have the floor, please.
Thank you very much. Thank you. I'll share my screen and let's get on with it. Yes, continue. Share. Can you see my screen?
Yes. All good.
Okay, good, very good. Right, okay. As already mentioned, my name is Panos Economou. I represent PE Mediterranean Acoustics Research and Development, and in collaboration with SoundZipper, I'm very happy to present here at BeyondX, Seeing Sound with Computational Acoustics. In this particular case, we're going to be using our product called Olive Tree Lab Suite. This is an overview of what follows. We're going to be seeing sound with computational acoustics. We'll be talking about why do we need acoustics, a brief presentation of ourselves, why we need another acoustical software in this world, and future prospects of computational acoustics. So let's see some sound. Here we have an industrial area, a port, and we have a residential area close to the port. And we want to know how is the noise port affecting the residential area. What we did in this particular case, we did a noise mapping that shows the higher the level of the curves, the colored curves, the higher the noise. It's just an illustration of what it is. We did say we're going to be seeing sound. I'm not going to go into any details, scientific matters. If you have any questions, I'm happy to answer them later. Here we see a wind turbine, and like what everybody thinks that sound travels in straight paths, when we have long distances, atmospheric effects like wind direction and temperature in the atmosphere change the path of sound. So in this particular case, we can see that the path is curved downwards. It can be curved upwards depending on the conditions. In order to be able to study the sound field around the turbine, we mapped around a single turbine, and we have taken into consideration these atmospheric effects, which are called in the technical terminologies atmospheric refraction. And of course, you can see that you can feel that the wind is blowing from the bottom of the screen towards the upper part of the slide. Of course, when we deal with, in computational acoustics, we deal with theaters. On the left, we see a model. On the right, we see a picture of a theater. We deal with sound reflections, for instance, from the ceiling. Let's visualize them. Here's some, and from the side view, to see the contribution of the ceiling in terms of reflections. We deal with highways and noise barriers. On the left, the noise barrier. On the right-hand side, it's a truck, which is occluding or obstructing the microphone with a transparent barrier. And this is how we calculate the paths from the engine of the truck, multiple reflections between the body of the truck and the barrier, and then the sound bends. This is what we call sound diffraction over the barrier in order to be able to reach the microphone. I'm going to be coming back to this truck a bit later on. Of course, we can deal with call centers because we see how sound is diffracted or bends over the panels or have reflections from various objects in the call center. Here we have home theaters, and this is a model of the theater view. The white lines represent the direct sound coming from the loudspeakers, and this is what a receiver or a member of the audience is receiving in terms of direct sound. And if you wanted to map sound in the audience area, this is the result. And you can also see the panel directivity. What do you mean by panel directivity? We want to check how a panel responds to when it receives sound. So in this particular case, we can see that there is a loudspeaker sending sound to the panel. And in order to be able to determine the directivity of a panel, how does it radiate, the panel, we have a microphone rotating around the panel, and the result is this. And unlike our expectations, we see a complicated pattern. It's not a smooth or regular pattern. How do we use this? When we model theaters, we want to see what is the contribution of individual ceiling reflectors in the audience, in the auditorium, and how do they distribute sound within the audience. One may ask the question, why do we need acoustics in the design and construction industry? I think the papers speak by themselves. We are overpopulated, and that brings us closer to each other. We have lots of noise sources and lots of noise paths. And acoustics is a big area, and it has lots of categories, fields, topics that deal with such noise paths. We have air traffic noise, we have road traffic noise, we have plant room noise, we have sound transmission among spaces, and so on. One of the fields of acoustic is called building acoustics, which deals with sound transmission between spaces. So when we're dealing with computational acoustics, we have to take that into account. Another field is what we call room acoustics. We put some soft materials there in this space, so we don't have to wear ear protectors and enjoy our meals. Another field of acoustics is noise control, which means we are devising methods by which to make sure that the tools we are using are not as loud when drilling outside our homes. We have environmental acoustics, making sure that noise industries are not affecting residential areas. We have underwater acoustics, we deal with marine life and submarines. We have psychoacoustics, a very important aspect of acoustics. And these are some of the fields that computational acoustics ought to be taken into account. This is why we need acoustics. Before I carry on, I would like to speak about our story. Myself, the companies, and the products. I studied mechanical engineering, and then I went into acoustics. I established Panacoustics in '82, a consultancy company. I was using third-party software, and I was trying to match my predictions with my measurements, and I couldn't do so. And I said, okay, if nobody's doing it, I'm going to do it myself. So I started PE Mediterranean Acoustics Research and Development, PEMAD for short, to do exactly just that. One of our products is called Olive Tree Lab Suite. It's called Olive Tree because it's considered in the Mediterranean area, ancient Greece, to be the tree of wisdom. And I'll explain a bit more about the tree part. It's called Lab because you have a laboratory on your laptop desktop to conduct your various experiments, as we can see later. And it's called Suite because it's an integrated environment. One does not need to go to third-party software in order to be able to solve some problems. So let's see the tree. Basically, our tree grows with time as we add more branches of acoustics, the various fields of acoustics. So we started with outdoor sound propagation, we went to room acoustics, with building acoustics, and atmospheric refractions, and so on. We also have what we call the Olive Tree Lab Acoustics Lib, which is a code, a library code that enables other software developers to create their own version of acoustical software, or other software developers to integrate it within their own application. And of course, we conduct research and we publish this study of an ancient theater in Cyprus, and the paper was published in 2012. And this was at the time we were conducting the experiment. Okay, another question. Why PEMAD or OTL Suite? Why do we need another acoustical software in this world? Okay. That was a very good question. We put that question to ourselves. I'm just going to give you the story. Computational acoustics started at the end of the 80s. Computing power was not available, and most of those computational acoustics dealt with standardized methods. By definition, standardized methods are the methods that one uses. Irrespective of who uses that method, one should be able to come up with the same result. That means that that method has to be simple. But this simplicity allows for errors. And if you see the graphs there, you can see on the left an ISO method, and on the right-hand side, our calculations with our PEMAD approach, and we can see considerable differences. So we decided that we are going to start. That's what we did with Olive Tree Lab Suite, our own software, which is based on first principles, not to cut corners, and using cutting-edge technology, implement our software. Now, we did talk about the track. I'm just showing just one path, going from the track, bouncing off the barrier, bouncing off the body of the track, and then bending multiple times, and then bending over what we call sound diffraction over the barrier to reach the microphone. It seems simple, but we are the only commercial software company that can do this kind of calculation because it's very complicated. There might be similar methods to calculate in some universities, but in terms of commercial software, no, we are the only ones. Just to show you another example of what it is that we can do, others cannot do, let's take, for instance, control rooms in recording studios. Let's talk about the mixing desk. Everybody thinks that, the bigger the mixing desk, the better the result. In fact, the mixing desk is an obstruction to mixing because you have, as you can see on the left-hand side, the direct sound reaching the microphone, and you have a reflection off the mixing desk. And when they combine, there is what we call wave interference. So, and it creates the comb filter effect. That's how it's known. Usual computational companies, acoustical computational companies can perform reflections, but we can also include edge diffractions, as we already mentioned, which is the radiation of sound from edges of an obstacle. So we can see that the sound field in front of the sound engineer is not at all plain. It's very complicated. And in fact, it's more distorted with the calculation of edge diffraction. I suggested actually in one of the papers when I wrote something about mixing desks that we have to replace, those who are manufacturing the mixing desks, to replace their mixing desks with augmented reality so that there is no object in between the loudspeaker and the sound engineer. I put up this slide because many of you are wondering what kind of approach do we have in order to claim that we are superior to others. I'm not going to be talking about technical terms. I just put it up because I know that this is recorded and one can look it up after the video is put up on BeyondX. If you have any questions, I'm happy to answer them later. Yes, answer to the question, why do we need another acoustical software? We need it because we have new challenges. We are depleting building materials. There are no, the resources of building materials are running very low, so we have to come up with new materials. Here we are seeing sand being mined from the sea and the rivers. The future, most probably, we're going to living on floating cities. If we do that, then we need light materials, but light materials are not very compatible with sound. And let's examine just to show you what I mean. This is a form that is integrated in our software that enables somebody to calculate the performance of a structure with the various layers. In this particular case, I took a dry wall of gypsum boards. And I've calculated the performance. And I'm going to compare now to the typical wall. The graph shows the performance of a brick wall and a dry partition. The higher the curve, the better the performance of the wall in terms of sound transmission. In the blue range, we see the base range of subwoofers. So if you are happening to be living in a building next to somebody who has home theater equipment, or he's a hi-fi enthusiast, it's better for you to have a brick wall rather than a dry wall, simply because the dry wall is not going to put a lot of resistance in sound transmission. And we're talking about walls of exactly the same thickness. So what's in the pipeline for us? New frontier. We are dealing with aircraft noise. It's a plane, and as we already spoke, long distances involve atmospheric effect, wind direction, and temperature gradients in the atmosphere. So here is the air traffic route, landing and departing from an airport. And on top of it, I superimposed some planes. You won't be able to see the planes because it's such long distances. So, but we can see the paths of the planes reaching houses. So we can see, as we already mentioned, curved paths. If we zoom into these paths, we are going to see a complicated pattern. And eventually, the microphone in that neighborhood receives some of these paths. Here we have a noise mapping around the airport, seeing the departure and the landing areas in yellows and greens. Now I'm going to be showing you a video simulating single airplane flight over a huge area, just to visualize what I'm talking about. What you see at the back, it's a mountain range. So what you have to pay attention to is that the lines represent sound waves, what we call wavefronts. And you're going to see that they're not very smooth. They're not smooth simply because they take into consideration reflection and diffraction from the ground or mountains. And of course, atmospheric effects like wind, direction, and temperature variations. Another thing that we can also simulate is the Doppler effect. The Doppler effect is the thing that you hear when a car is approaching and passing by you. At the beginning, it's a high pitch, and at the end, it's low pitch. It sounds like, and allow me to experiment with that. it goes like, hmm. So the pitch goes down as it passes by. So we can simulate this effect with the compression. We can see that the front wave, the waves in front of the aircraft are being compressed. That's why it's a higher pitch. And the waves at the back of the airplane are at a bigger distance. So let's watch the video and watch the green and yellow patches to see the Doppler effect. Right, what else is there in our pipeline? Entertainment is something which is very relevant nowadays because the loudspeakers are very powerful. And to demonstrate that, we took a hypothetical situation in the Wembley Stadium in London, which is famous for its concerts, and we modeled it and we put it on a Google Earth map, and we are simulating what would happen when we have concerts. If we assume no atmospheric effect and we have two receivers, two microphones, one close to the Wembley Stadium and one far away, you would expect to see, without atmospheric effects, straight lines. But in fact, we see a much more complicated pattern. If we were to map the area, this is 2 kilometers by 2 kilometers, that area. The left is without any atmospheric effects. On the right-hand side, we can see the atmospheric effects. And you can feel that the wind is blowing to the right. You can feel that the sound is being pushed towards the right by the wind. Another thing that we have in mind is sound rendering, a bit relevant to the previous presentation, which was an excellent presentation. And this is the last topic I'm going to be talking about, and I'm going to receive your questions and answer them. So by definition, sound rendering is the process of generating the sound of a source in a 3D space in such a way as to simulate listening experience at a given position in the modeled space. Now, we're claiming that we can do that better than the others simply because we take into consideration a lot of effects that are taking place within a room. I'm going to be showing you the process, and I'm not going to be commenting on how it's done. I'm just going to be highlighting something. Watch the allow this imagination, experience, intuition, real world data. There is a sound engineer who is going through all these chain of events, and he's controlling eventually the acoustics of the scene he's visualizing for videos, for movies, for animations, for reality, virtual reality, augmented or merged reality, and he imagines how it ought to be. What we are proposing is to scrap that, and instead of that, use what we call OTL Soundscaper, which is able to compute the acoustics of the environment, so he doesn't need to think or imagine or make mistakes of how realistic that sound ought to be. So at that point, I'm going to leave you and thank you. I would like to thank once again BeyondX for giving me the opportunity to present here, and also Sound Zipper for our collaboration. Ready to take your questions.
Thank you, Panos. Thank you so much for a wonderful presentation. Now, I'd like to call upon the audience to do a poll. We're going to launch a poll. So while we are doing the discussion and the Q&A, please do join the poll so that we can we know what you're thinking about. What are your thoughts? What are your what's your vision? What are your constraints and all that, so that we can couch the discussion and the Q&A better. Before we start the discussion, please allow me to just recap, quick recap of sort of a quick summary of what Panos has presented. Now, he spoke about atmospheric effects on sound, that sound doesn't necessarily travel in a straight line, and various applications in theaters, noise barriers, very important application, call centers, home theaters, aircraft noise. He spoke also about computational acoustics, different types of acoustics, room acoustics, noise control, environmental acoustics, underwater acoustics, and psychoacoustics. And this is peculiar to Panos. He has his PIMAT scientific superiority in acoustical computation. And especially interesting as we move forward would be things like environmental noise, sound rendering, a very exciting concept of sound rendering. And the other one would be the use of the OTL sound scraper, which is a proprietary product of Panos, in game and animation sounds and creation of sounds, essentially. Simple, easy creation of sounds. I hope I got that all all summarized nicely. Now, okay, so the poll's running, and perhaps Joe, would you like to chair this segment on the discussion?
Sure. Thanks, Panos, for your wonderful presentation. I will throw in my question first. First of all, SC Design is a specialized unit under the ONG&ONG umbrella that deals with offices. My studio in particular also deals with homes, landed properties. So many of my clients, be it from the office clients or the homeowners, they have been asking us, what happens to the post-COVID world? How are we going to design differently to accommodate the post-COVID world? Well, as a designer, there are obviously a lot of direct ideas that we can think of, like sound booths, definitely more teleconferencing, or at homes, you probably design a little bit more for comfort. Maybe you can even have your theaters for like home theaters for bigger homes. So how does your software can help to shape and for the post-COVID world to help to make people's life better in this constant pause and go kind of situation? Yeah.
Well, I think the designers ought to be able to take acoustics, let's say, more seriously. Not to give the emphasis only on just the visual aspect, but also the acoustical aspect. I mean, if you looked at, we watched, it's a very impressive presentation from Unreal Engine, and I didn't see any reference to sound. Everything is visual. I mean, we're the poor relatives of technology, and it's simple. It's because acoustics started about 100 years ago. Not many people are aware of what acoustics can do, and there have been lots of mistakes, and it used to be called the black magic. Not everybody gets it right. So that's why we came up with this computational acoustics, our software, So the purpose is to be able to, in your case, if you have a space, to introduce it into our software in terms of a DXF file or the AutoCAD format, and then with manipulation of the properties of the materials, you ought to be able to instantly have a feel for it. It's not going to, it doesn't take long. You don't need to do very complicated calculations, because what you're referring to is mostly room acoustics, which is reverberation time. And reverberation time is a very simple formula to apply, and you can easily get the result. And I would strongly recommend that you use computational acoustics, irrespective, not ours, any other acoustical software, to be able to deal with reverberation time to make it more comfortable.
Okay.
I hope I have answered the question.
Yes, definitely. I think what you have said is definitely true. We have to take acoustics seriously, and not just thinking about the looks and all. Yeah, really.
Yes, exactly.
A step further, yeah, and dive into the real gist of it. Yeah.
Yeah.
Shall we proceed to the questions that are being handed out by the audience?
Yes, please feel free to lead us through the questions. Yeah. I think there's some. I think we've got some questions in the Q&A tab.
Yeah. First question from the audience: how easy is it for designers and architects to pick up the use of this software? Does it have a steep learning curve? If I may just add on to this question, can it be integrated to BIM? Because that's what we are moving towards too.
Well, that's a very good question. We did try to, we started later than the others in terms 2009. The others have already built their technologies based on something old-fashioned, let's say. So we were inspired by SketchUp, and basically what you do is, as I said, you introduce the model into the software, and then you manipulate the materials. Now, learning curve. It can be easy and it can be difficult. It depends how deep you want to go, because one of our principles is to allow the user to go as deep as they want. We don't want to exclude high resolution analysis, high frequency resolution analysis. Others only do third octave analysis or octave analysis worse. So we do a very high frequency analysis. We go from 0.1 hertz to 100,000 hertz. We do peculiar stuff. So basically, that's why we have clients, universities that are using it to demonstrate to their students. For instance, one of our clients is the Architectural Association in London, and it's a very prestigious university, and we are very honored to have them as our clients. The answer to that, it depends how deep you want to go and how much background have you got in terms of acoustics. One needs to be aware of acoustics, not to expect and to be a bit critical about what the computer says, because if you don't put the right conditions, then you might get the wrong answers.
I see. Then in that case, just a follow-up question, will you conduct trainings for interested companies, or is there a way to learn from you?
Yes, we do. In fact, in the past, we had an acoustical festival, not just about our products, but we wanted to propagate the acoustics in general. And we do have training sessions, we have webinars, and anybody who wants to learn, we provide support. I think our friends in Singapore, Sound Zipper, can verify that.
All right. Cool. Okay, one more question from the audience. Are we right to assume that the software can be used for commercial, residential, outdoor, and indoor projects? All sorts of projects?
Yeah. Yes. Of course, it deals with outdoors and it deals with indoors. Basically, we do not. The integrated part of our software implies that we don't separate sound into indoors, outdoors, and so on. It's just sound propagation. Now, whether it meets atmosphere or whether it meets a wall, that's another question which we handle accordingly, according to what the sound path discovers on its way from the source to the receiver.
I see. All right, one more question from the attendee. So again, it's related to the post-COVID world. Many of the design is being encouraged to be more naturally ventilated instead of having the centralized air condition. We try to improve the airflow. So when we improve the airflow, generally the outside noise will come in and it tends to be noisy. So how do you think that we can make use of your expertise to in a little bit more elaborate way to help with to deal with this noise that's from the surrounding context?
Well, it's a very good question, actually, because once you open the windows, obviously the sound is going to come through, and then one needs to come up with some solutions, and that's what we call noise control, the area of noise control. Making sure that for instance, in Europe, they use double glazing, and they have openings at the top and openings at the back, so at the bottom, and we're talking about the cross section here. If the sound goes through that passage, then it's been absorbed and we attenuate sound. Now, as far as our software is concerned, yes, you can carry out some experimentation and see how well those designs, or how much can one improve particular designs. So yeah, it helps, but it doesn't give answers to all of the problems that, because as I said, we still develop more and more. For instance, another thing in our pipeline is duct-borne noise. In other words, when sound is traveling, noise is traveling through the ducts from one place to the other. We haven't implemented that, even though we have worked on that. It's in the pipeline too. As I said, our tree is still young, it's growing.
I see. So one more question from the attendee. Will we see you include ACMV in OTL? I assume it's the testing of ACMV noises.
I'm sorry, can you repeat the question?
Will we see you to include ACMV, air conditioning?
HVAC.
Yeah. Right. Yeah. HVAC. Yes. Yeah. Well, that's what I just mentioned. That we have already developed the HVAC approach. It's just that we haven't implemented it yet. We have also developed the building acoustics part. Now, it's very easy for us to do, to implement such methods, the standardized methods, but we don't want to do it the standardized way. Mm-hmm. We want to do it the proper way. Allow me to explain how I see building acoustics. When we calculate building acoustics, we say, okay, the level inside, we have a loudspeaker, and we calculate the level, and then we have a big area on the wall. We calculate the area of the wall, and then we assume that the wall is radiating in the other room and so on. And we have simple formulas to do that. But as far as I'm concerned, this is very, very simplified. There are refraction effects. The wall has it's a different medium. So whenever you have a different medium, we have refractions. Like when you look at the lake and you're trying to see the fish is not at that particular position you're seeing, it is somewhere else because there is refraction. So I would like to include refraction in our calculations. And not only that, I wanted to be able, if you have dry walls, to be able to detect, oh, here I have a metal stud, here I have a rock wool, here I have a panel, and go through all these critical paths and then say, okay, I'm coming out now from the final layer, and then I'm going to radiate according to the panel vibration. Now, that's a very complicated calculation. It's not very easy. It's not easy at all. So that's why we are still working on building acoustics, because we have a particular way of approaching it. We don't want to do the standardized method. Otherwise, it's very easy to do. One can use simplified methods that others sell.
I see. Understood. We have one interesting question from the audience. Mr. Panos, you mentioned 0.1 Hertz to more than 100,000 Hertz. So his question is that this range is outside of the human hearing range. Can you tell us what application is this wide frequency range for?
Well, one day maybe we are going to be dealing with earthquakes. Mm-hmm. So earthquakes we're talking about very, very low frequency ranges. I mean, we don't exclude the possibility. I told our developers from the very beginning, if we're going to do this, it has to be very flexible. So we have included a huge range to be dealing with supersonic sounds and low infrasounds, like in the case of seismic waves and things like that. So it has that, it allows already the flexibility for future applications. Maybe one day we're going to be dealing with radio waves, which are much higher in frequency and so on. So that's why I've mentioned that particular frequency range.
Right. Okay. Next question is an important one. We know that you have partnered up with SoundZipper in Singapore, and interested companies will be contacting you guys. So the question is, can your partner in Singapore do all that was being discussed in your presentation?
Yeah, because they are already using our software for a long time now, and they are well trained, and in case they run into any peculiar situations, we can always support them.
Cool.
Hi, Panos. I've got one very burning question, if I may just pick your brain. Now, we in AEC, in architecture, engineering, construction, and construction, we do a lot of BIM, building information modeling, which I'm sure you're very familiar with. We're just wondering how difficult or how easy it is to integrate sound engineering and sound engineering software together with our BIM software, like Revit, for example. How is that process? What's that process like?
Well, it's a very good question. I was really impressed with the previous presentation. And the reason we have available our acoustical library is that it enables developers to integrate it within their own software. So what we are proposing is that all you have to do, instead of you having to start from scratch, we can provide all these difficult calculations. Just to make a point, every time we calculate a reflection, the others are saying 1 minus the absorption coefficient of that material. In our case, it's a very long asymptotic equation. It takes a very long time to calculate, relatively long time to calculate. So the point I'm trying to make is that it involves a lot of complicated calculations. So all they have to do is take those ready-made classes, I don't know what to call them because I'm not a developer, computer code, and integrate it into their own system, because we have that platform that allows the integration of our software in other softwares. So I would guess that's how it ought to be, because we cannot develop a plugin for SketchUp, for Rhino, for Beam, and so on. I mean, even though it'd be nice, but we don't have the resources.
But the OTL sound scraper should be able to do that, whatever you mentioned, right?
I'm sorry, can you repeat the question?
The OTL sound scraper, the OTL sound scraper should be able to do what you mentioned.
OTL scaper. It's a soundscaper.
My apologies.
Yeah, soundscape. It gives us soundscape of the.
Yes.
Yeah, right. We have experimented with real-time calculations of moving sources within a building environment, and we have the technology to do that. Of course, we have to find interested parties in order to be able to develop it more. It's difficult to claim that you have something which is so good that the world ought to be interested. And that's why we are very appreciative to BeyondX that gives us the opportunity to demonstrate that. We have videos to demonstrate such possibilities also in real time.
Fantastic.
Of course, the real time thing is not as effective as the proper sound rendering. I mean, the visual rendering is as complicated as proper, I suppose, proper sound rendering.
Because of the higher computation, the longer computation that you require. Yeah, that's right.
And we have also developed graphics card, GPU. We have developed such technology to be able to use the graphics card. But at the time we developed it, it wasn't a uniform standard as to which computer is going to be using what. So unless there is a standardization of that, we are not able to utilize that. So we have done a lot of things. There is a lot of things in the pipeline. I just don't want to show and overload those who are following with something which is an unknown subject like acoustics.
I understand. Last question is, no, having had, I mean, it was a wonderful afternoon. You kind of gave us that awareness, and you planted a seed in our heads that we can actually visualize sound, and that's very profound. I mean, from your vision, right, having the ability to visualize sound, to see sound, as it were, how then do you see the world changing in the next couple of years? You know, how should the world change with this vision that that we can see sound now?
Right. I'm not quite sure as to the exact point of your questions, because it opens up a few ideas. But do you want to be more specific before I answer? Okay. Not to talk about something which is not relevant to your question. How do I see the world visualizing sign?
Yeah. No. Okay. For instance, now that we can. Yeah. So what the stuff that we do every day when we design architecture and engineering and all that. So how does that change the way we design architecture and engineering?
Yeah.
Now that we can see sound.
Yeah, well, I mean, the previous presentation talked about, it was mostly about the visual aspect of it. It ought to be integrated in sound ought to be integrated in that, so that you are able to hear before you even build and get an idea as to what it is that you want to do. For instance, my suggestion to the mixing desk designers to make their desks obsolete, the actual furniture, and turn into augmented reality to be able to control with augmented reality all these filters and dynamics and so on. It's another suggestion. I mean, there is a lot of ways that one can utilize technology nowadays to be able to assist. Of course, one thing I always say is that computers won't give you the answer. One has to be critical about what you get, because we trust computers more than we trust our judgment.
Agree. That's therefore the notion of the experiential aspect of architecture, which is empowered by acoustics and sound.
Yes.
Very important. Yes. Joe, back to you, Joe. Any last observations?
No, all good. Thanks for a wonderful presentation. And we have answered most of the questions from the audience. And yeah, we hope that the audience have found something new, learned something new from today's session. Yeah. So we'll be wrapping up this session. And thank you for Mr. Panos for your presentation, and thank you, audience, for for being with us. Do go ahead and check the event schedule for other interesting and informative BeyondX sessions. So on behalf of my co-moderator, Mr. Lee Hao, we'll see you in the next cycle of BeyondX next year. Thank you.
We see you tomorrow morning, guys. Tomorrow morning we start off at 10 o'clock again. Yeah. So please join us tomorrow morning. Have a good breakfast, and we hope to see you right after breakfast. All right. Thank you so much. Thank you, Mr. Panos. And Joe, thank you so much. Good evening. Have a wonderful evening.